Okay, hello, welcome to part 3 of our A-level look at waves. So we started off a couple of lessons ago, we were looking at progressive waves. That was our longitudinal transverse waves, looking at wavelength, time period, frequency, things like that. Then last lesson we were looking at longitudinal and transverse waves, the differences in there. Now today what we're going to do is we're going to do a continuation of something we introduced at Key Stage 4, which is refraction. And we're also going to look as well at this total internal reflection. These are both things that were looked at Key Stage 4, but we're going to go into a little bit more detail this time around up to A-level, and we're actually going to do some maths and work out the, have the formulas and work out our refraction and something called refraction index as well. So, first things first, there's 3 things that can happen when light hits an object. The first one is reflection, so the light can reflect back off the object. This is where we have our angle of incidence, which is equal to our angle of reflection in comparison to our line of normality. You should remember that from Key Stage 4, if not, it's worth having a little quick look back at that. Number 2 here is the one we're actually going to be looking at today, which is something called where light transmits through an object, or it passes through an object. Now this is the point where waves can bend and we get our refraction. Again, the basics we did go through at Key Stage 4, but we're going to go into a bit more detail with that today. Our third one, just quickly, is where light can be absorbed by the object. A good way of explaining this, I suppose, would be when you think of X-rays. So X-rays have a good property in terms of the fact that they can pass through the soft parts of our flesh quite easily, but when they hit sort of denser material like bone, the bone actually absorbs the X-ray waves. So this means that when we get a picture from it, it is that contrast of where the waves have passed through and where the waves have been absorbed by the bone. So that's absorption. So today we're going to mainly be looking at refraction. So this is where the light transmits through. Now this is our basic diagram that we had back at Key Stage 4. There's nothing here that should really be that much different to you. We've got the angle of incidence. Again, this is our line of normality that we had at the very beginning. And obviously, instead of our light actually reflecting off like we were talking about and discussing with reflection, where we would expect it to be coming off somewhere like that angle, so these 2 angles are the same, what it's actually doing is passing through the object itself. So what's actually happening here is as it passes through the object, you can see that the angle is changing. This change is what's called refraction. The only thing that's different here from this picture, from the Key Stage 4 picture, is where we're talking about something called the emergence angle as well. And this is where the light comes back out from our denser material back to our air again. Now if you remember from Key Stage 4, the reason why this is bending is all to do with the densities of the medium that the light's travelling through at the time. So light travelling through air travels at the speed of light, surprisingly enough. It travels at roughly around 300 million metres per second. So when it gets through a denser object, it actually slows down because it's more work for it to get through that object, so therefore it has to slow down. This slowing down actually results in it having to bend through the material but closer towards this line of normality. If it sped up, it would move away from the line of normality. If you think about when we were talking about longitudinal sound waves, when they go into a denser material, they actually speed up because of that vibration. So they would actually move away from the line of normality. But with light, as it moves into a denser object, it slows down, so therefore it moves back towards the line of normality. And then again, the opposite occurs here when it goes into a less dense. So it's going from a dense material to a less dense material, which is air, so therefore it's speeding up, so it's moving back away from that line of normality. And remember, the line of normality is at 90 degrees to the material surface, not 90 degrees to the angle of the light. Okay, so refraction on a plane. Now this is our typical image of a prism. So what we've got going on here is where we said before is our dispersion of white light, which is where our white light is getting diffracted in this prism and being split into its different frequencies. Now that's the important thing to remember, is that the frequencies still stay the same, but we know that the speed is reducing. So therefore, if you remember our equation pyramid, where we've got speed is with the frequency and the wavelength, so therefore speed is equal to the frequency times by the wavelength. which don't forget, wavelength is this lambda, this numeral for wavelength, which is lambda. So therefore we know that the frequency is staying the same because it's the frequency that gives the light its colour, and it gives it this property of these colours. So therefore the frequency must stay the same, but if the speed is reducing, then the wavelength must be reducing as well in order for that equation still to work. So remember, it's the wavelength that's reducing, so the speed is reducing, but the frequency is staying the same. Okay, so this brings us on to what we were talking about, what I mentioned at the very beginning, which is this thing called the refraction index. So the refraction index of a substance is basically how much or how far it would refract the light as the light travels through it. So as our light comes into our surface and goes into our material, depending on the refractive index of that material will depend on how much that light bends. And now this is all to do, this is called Snell's law. Surprisingly enough, it's a guy called Snell who created them. So there is Snell's law, which is basically working out the refractive index of a material, and then there's using that refractive index to predict how the wave exiting a denser material would alter the angle as it exits that denser material into a less dense material, but we'll get to that. So basically, Snell's law says that the refractive index is the sine, so we're getting into a bit of geometry here, is the sine of the incident angle, so remember that angle from the angle of the beam in comparison to the line of normality, divided by the refraction angle. So that is the angle of the actual beam as it's travelling through the object, again in relation to that line of normality. So what we're going to try and do is actually go through, or say we're going to try and do, what we actually are going to do is we're going to work through the maths so we can actually figure this out. So what we've got here, in case you can't quite see, because I know it's quite a dark picture, is that we have here, this green line depicts a glass block. And our red line here and our red line here is our light beam as it hits our object here, and this refracted, which is our blue line is our line of refraction as it goes through the object and exiting again when it gets to the red object. So using Snell's law, we know that the refractive index is equal to the sine of the angle of incidence divided by the sine of the angle of refraction. So therefore we know our angle of incidence here because we've got our line of normality set up in 90 degrees to the edge of our material and our light beam coming in here. So this angle here we know to be 48.5 degrees. So again we've then measured our angle of our light refraction. So we've carried on this line of normality into our glass block and then followed the refracted light across. We know that that angle is 33 degrees. So hopefully you've all got your scientific calculators out with you. If not, this would be a good time to go and get them. So the refractive index is the sine of the angle of incidence divided by the sine of the angle of refraction. So depending on your calculator, you'll either have to type in the angle first or you'll have to press sine first. With my one, I have to put the angle in first. So the sine or angle of incidence, which is 48.5 degrees, so you press 48.5 and then sine, or sine and then 48.5, depending on how your calculator works. And then we're dividing that by our other angle, which is our angle of refraction, which we have 33 degrees and sine. So this gives us an answer of 1.375. So now that is our refractive index. This basically means this will always be greater than 1. Okay, the refractive index of a vacuum, so someone that has no gas, no air, no solid, no nothing in it, the refractive index of a vacuum is 1. So therefore, everything else is going to be denser than a vacuum, so therefore it's going to be greater than 1. For example, air, the refraction of air is 1.00029, so it's really, really close to a vacuum. So this gives us a refractive index of our material. So then what we can do now is go on to our second image, and all we've done here now is actually taken our glass block and we've just rotated it so it's now at a greater angle. We've not changed the light, we've not moved the light beam, all we've done is move the block. So now our angle here, instead of being 48.5, is now 74 degrees. So what we can actually do is use Snell's law, and we know that our refractive index is equal to 1.375. So using, if we get our pyramid out, if we get our pyramid equation out. So we know that the sine of the angle of incidence, you have to divide that by the sine of the angle of refraction to be able to get the refractive index. So we know our refractive index and we know our angle of incidence, but we don't know our angle of refraction, and that's what we want to work out. So we block that out, so that then means that we actually need to divide the angle of incidence by our refractive index. So our angle of incidence is 74 degrees, so therefore our angle of refraction is going to equal the sine of 74 degrees, and it's that divided by our refractive index, which is 1.375. So if we do that, again, you should have your calculators out. So it is the sine, it's 74 degrees sine, again you may have to do yours the other way around, and it's that divided by our refractive index, which is 1.375. Now that equals 0.699. Okay? Now don't forget, now I know some of you will probably be sitting there saying, well, how's that possible? That's not an angle. You're right, it's not, it's very, well it is, it's a very, very small degree of an angle, but what it actually is the sine of our angle. So don't forget that all of this is working out the sine of the angle of refraction, because it's the sine of the angle of incidence, the sine of the angle of refraction. So in order to actually make that into our angle, we need to do something which is called inverse sine. It's a bit like square rooting a number. When you square root a number, you get a much smaller number. What we actually want is that original number that we square rooted. So therefore, what you need to do is you should somewhere on your calculator have a button that has three letters, INV. Alternatively, there'll be a function button that has sine and then a little -1 next to it. That is what you need to do. So in my one, it's inverse and sine. And what that does is then inverse that number out, and what you end up with is 44.35, and that is in degrees, and that is actually what our angle of refraction is here. It is 44.35 degrees away from our line of normality. So that's how Snell's law can help us to not necessarily just work out the refractive index of the material, but also then use that to work out how the light itself would refract through that material once you know the refractive index from there. So, if we then go back to our presentation, or my presentation even, we will then go on to Snell's second part of his law, where this actually gets to explain how we can take the material from a dense material, we can take the refractive angle from the dense material, take the refractive index and that angle, if you multiply those together, that will then give you the side angle for how the light would pass out into the lesser dense material. So what we can do is, again, we can go back to our pictures. If I go back here and I clear all this off, what I'll do is actually I'll just rub it off, it'll probably be easier. So we know that our refractive angle is 44.35 degrees, which is this 44.35 here. So what we need to do is that when it works out is that you take the refractive index, which is 1.375, and you multiply that by the sine of our 44.35 degrees, and then when you do that, so we take our 44.35 sine multiplied by 1.375, which gives you 0.96. Now again, this is 0.96. Now this is actually, again, the sine of our angle. So we need to inversely sine that, which gives you 73.98. Now, if you take that 73.98, this is not taking into account that obviously we're moving it into a different medium. So if we had that 73.98 and we multiply that by the refractive index, and the refractive index of air, as I said earlier, is 1.00029, that gives you an answer of just over 74 degrees. So considering we're rounding up numbers, our angle went in, which is 74 degrees. We'd expect our angle coming back out to be 74 degrees as well, because all the light is doing is travelling back up to the speed of light in air. So therefore we would expect the angles to be exactly the same here, and that's exactly what is happening. So all we're taking is our refractive index of our denser material, multiplying that by our angle of refraction. That then gives us an answer which is the sine of an angle. You inversely sine that number, which gives you the 73.98 which we have here, and then you multiply that again by the refractive index of this material. Therefore what you have is 74 degrees. So that is the second part of Snell's laws. Now, after going from here, we were going to discuss what is called total internal reflection. Now, total internal reflection, as we were talking before, is where actually where the line actually stops refracting back, and what it actually does is reflect off the inside surface of the material. So what I'll try and do is explain exactly how that works. So if I get a clear page here. So what we're generally talking about is we take a semicircular perspex prism. I know my drawing's not amazing, but you have to bear with me. And this is our line of normality, okay? So if we say that this has the same refractive index as our glass block had earlier, so our refractive index is equal to 1.375. And Snell's law says that the sine of the critical angle, okay? So the critical angle is when we have a line, if we have our light beam coming in here, and it refracts out, we'd expect it to speed up to come out. So it speeds up coming out into the gas. Okay. Now the critical angle is the angle at which our light goes into this point and no longer refracts back out into the air, but what it actually does is continue along at 90 degrees. So it actually travels along the edge of that perspex, and that is called the critical angle. So this angle here would be classed as the critical angle, and in order to work that out, you need to divide, or the way that it's written is N2 divided by N1, okay? Now, all N stands for is the refractive index, okay? So what we're taking is we're taking N2. N2 is what is refracting into. So N2 in this case is air. So therefore our refractive, to work out our critical angle, so our critical angle, or the sine of our critical angle, okay, so that is equal to the refractive index of air, which is 1.00029, divided by the refractive index of the material that it's going into. So we're saying that this is the same refractive index as our glass block. So that's divided by 1.375. So again, it's calculator time. So what we're taking is 1.00029 divided by 1.375, which equals 0.72. Again, this is the sine of our critical angle. So our answer at the moment is 0.7, well, it's 0.73, isn't it? Because you round that 7 up. But again, that's the sine of that. So we need to inversely sine that, and that gives us a degree, a measurement of 46.68. Again, we're rounding that 7 up, and that's in degrees. So that basically means that if we had a semicircular prism with the same refractive index as our glass block, it would mean that once this light, the light beam that we've got travelling here at the moment in green, just draw those lines again that I've rubbed on. So this basically means if we had a light beam travelling in here and our angle here was 46.68 degrees or higher, then our light will actually reflect back instead of refracting through. And this is what total internal reflection is. It's an angle that is greater than the critical angle, because that then means that the light reflects back off the inside section of this plane section of the prism that we have. And that's what total internal reflection is. And there's many uses of those, from the medical, from medical science, through to the way that we get broadband, the way that we have our internet, the way that we get our digital TV. A lot of it is through this optical fibres now. And it's made from, this outer section is really non-reflective material, and then inside it is the mixture of 2 or maybe more different types of glass or perspex that have different refractive indexes, and depending on those refractive indexes determines the reflective angle that goes inside the tube. So it can be adjusted for speeds, for how fast that you want it to travel. And that's exactly what total internal reflection is, just using and reflecting light inside, and it can be used in information technology and can be used for medical purposes, for exploratory examinations. So that's our look at refraction and total internal reflection. We've looked at Snell's laws, we've looked at critical angle, and we've gone through some of the maths as well, so hopefully that is not so alien to you anymore. That's the end of today's lesson. Our next lesson, as it says here, is all about superposition of waves and what stationary waves are. Yeah, my name's Ian McDowell, I'm a student at Brighton University.